Recording is rolling. It is Monday, November 4th. A bunch of guys just turned in your quiz. This is for circular motion, centripetal force, gravitation orbits. So I'll grade those pretty soon. We're starting on a new topic today, energy, work, and power. So those thumbnail notes I gave you guys on the very first day of school, we're moving on to the green banners. I should get to go through these posters to go through this topic poster by poster. So look for the green banners to help you guys out. Got them hanging up in my room too. All right, so real fast, I'm doing one video for all my classes here. AP Physics. Oh, you guys have open AP Classroom Unit 3. I do have a tentative due date about 8 days from now. And then all my classes have new puzzles, so I'll flash them up here real fast. My college physics class has chapter 5. My honors class has chapter 10 and 11. Got some there. My conceptual students from their book is chapter 7, right? This is all energy, work, and power is what this is. Energy, work, and power is what we're doing. All right. Oh, and one more thing for my AP students. I did check on this because there was a question. So they made a new AP exam for this coming year. It's going to be a new format. It's going to be digital, but only the first half. So it's 2 halves. The first half is multiple choice. That part's digital on a laptop. The second half is free response questions, but it says here students will handwrite their answers to your free response questions. Again, that only counts if you're AP. If you're not AP, don't worry about it. You're AP, got it. All right, so got that. Okay, I have a video for you guys that we're going to get to kind of by the end of class today. So you guys ready for a video? Here we go. Also, this gave me a little bit of trouble. So, all right, so guys. You guys see how small that video is? That's as big as I can get that right now. So you guys get one shot to watch this also. You guys see that bowling ball at the top of the track? See the bowling ball at the top of the track? All right, I'll watch real close. What's gonna happen? I can't really fast forward or anything, so sorry about that. Just hang out here. Okay. Possibly by the end of class, we'll be looping back around to this. Oh, look at that. Look at bowling ball. Oh no, that guy's in there. Oh, wait, he's all right. Okay, he's got a helmet, but the bowling ball made it around, right? Hey, I remember a question coming up in the last couple of weeks about what's the minimum speed for that bowling ball to make it around, right? So don't crash down on his helmet head. What's the minimum speed? Well, this week we're going to extend that question one more step. We're going to say, well, what's the minimum height that you had to drop that ball from in the first place so that it has that speed so that it can get around the loop, right? Is that? And so possibly by the end of class, we'll start touching on that. Let's bump this out of the way. Point. All right, we're back to here. Oh, actually, there is one more thing I want to show you guys. All right, I have to Google this. All right, guys, so same thing. When I drag something over here, I can't really affect it. Well, I guess I can scroll a little bit. That's about it. Sorry, I can't make that window any bigger. But my Google search is perpetual motion machine. You guys see this right here? I see all kind of funny looking contraptions. They look like Ferris wheel type. A lot of them do. I see bearings. I see. Oh, okay, well, that's right. Oh. Hey, can you build a machine that you could just like maybe have some bearings, maybe some magnets, and set it in motion, and it just goes forever? Can you do that? Is that a thing? No, you can never build one of these. Right? It'd be really nice if you could, because if you could hook this up to a generator, and you could just create energy, all the electricity you need without any energy input. Guys, the energy in this room, what's the source of most of the energy in this room? That's lighting the lights, the air conditioning, the projection. It's coming from what? True, generate electricity, but what's boiling the water that's turning the turbine that's allowing that process to happen in the first place? It's coming from where? Combustion of what? Natural gas. Guys, most of it's natural gas, a lot of it's coal. There's a little bit of wind, a little bit of solar, about 20% nuclear, but that energy comes from somewhere, right? Could you just rig up a machine that just runs it on itself and doesn't have it? No, you cannot build one of these. It's called a perpetual motion machine. But actually, this is one of the ways I got really good at the class. There's a few ways, right? Sitting down, solving lots of puzzles, that you'll get really good at any subject. Helping each other out. That's why I have you guys, lab partners or in desk pods, right? You guys can help each other out, right? Because if somebody asks you a question, you have to be able to articulate that. You have to really know deeply what you're talking about. So that helps, right? But also this, back when I was in high school, one of my projects that I like to do in my spare time was pull out some craft sticks and some magnets and some bearings and hot glue gun and see if I could rig up one of these perpetual motion machines and make it work. Of course, I never did because there's a principle in physics called conservation of energy, which is this, that you cannot create or destroy this kind of abstract unit of nature, this variable called energy. This right here, energy. Right? However much energy there was in the observable universe, say a billion years ago, is the exact same quantity that there is today. Is the exact same quantity that there will be a billion years from now. The quantity of energy does not change. Okay, so here we go. I got a list for you guys. Some new variables you got to see, what they refer to, and what unit we're going to measure these in. Guys, look at this J all over the place. What do you think the unit J stands for in this class? Joules, exactly. And I'll show you guys what 1 joule is. 1 joule, right, as a unit, this is SI unit, breaks down into 1 Newton times 1 meter, right? Oh, kind of like, hey, Newton's measures force, right? What if you push on something with 1 unit of force for 1 meter? That's like transferring 1 joule of energy. Right? And Newton is a composite unit. That breaks down to kilogram meter per second squared. You guys know that from Newton's second law of motion. F equals ma. Combine it with this mass, or meters. Sorry, oops, this M is meters. Right? Put it all together. You get this. Kilogram meter squared per second squared. That's what 1 joule is. And like I said, in the observable universe, however many of these there were a billion years ago, exact same quantity that there are today, exact same quantity there will be a billion years from now. You cannot create or destroy this. What's running everything in this room right now, all the lights, the air conditioning, the projection that you can see right now, right? It comes from mostly natural gas, but probably about 20% nuclear and a few other sources. The energy had to come from somewhere that eventually boil water, turn a turbine, get it on the electric grid, and then run everything in here. It comes from that. Right? All right, so you guys get with energy and joules? Okay. Now, energy can take lots of different forms. We'll look at these in a few minutes, but I want to skip down here a little bit to look at this power measured in, what do you think this capital W is here? Watts. That's right. You guys ever look on a light bulb? It says like 40 watts on it, right? Now, don't confuse that with, guys, look at this capital W over here. Guys, there's 2 capital W's on this table, and they mean totally different things. Right? I'm helping you guys out. Don't get mixed up, right? Capital W as a variable means work, which is a transfer of energy. If you push something for some distance, 4 times distance, that's what work is. Now, that's also joules, because that's measured in joules, because that's a transfer of energy. This capital W down here quantifies power, right? It stands for watts. So power is so many watts. Okay, so what is power in watts? Well, I got it right here. Right, so 1 watt as a unit, that's 1 joule per second. All right, if you can read the music of these units, that tells you what power is. It's a rate transfer of energy, isn't it? Joules per second, that's like energy per time. If you have a 40-watt light bulb, so you have it plugged into a flashlight, is that drawing energy from the battery at 40 joules per second? Yep, that's what 40 watts means. Or suppose you have a 40-watt bulb plugged into a light socket, plugged into the electric grid. It's that 40 watts would be pulling 40 joules every second off the grid. You see that? All right. And then since joules breaks down to all this fun stuff, combine it with this per second to get 1 kilogram meter squared per second cubed. That's what 1 watt breaks down into. Right? So we're getting deeper into the semester. These units are getting more complex. But do you guys see that so far it's still the same 3 ingredients? It's just kilograms, meters, and seconds. Right? You guys see that too? So that's kind of interesting. All right, guys, good so far? Good so far? All right, because I want to look more detailed. They actually have a better poster for a bunch of these. Guys, energy can take lots of different forms, but there's just a handful that we care about in this class called mechanical energy. So notice I don't have anything about chemical energy stored in a AA battery. Right? Guys, a battery maybe only lasts a few years, and then you have to swap it out with a new battery. Maybe that's a hint that there's only some amount of energy in that battery, which is finite, right? There's you know what else I don't have on here? I don't have nuclear on here. I don't have energy in a gallon of gasoline. You guys have to keep going to the gas station, pumping gasoline to make your car run. I don't have if you ate breakfast this morning, that's a type of chemical energy, right? So that's not on here, right? But I do have these mechanical forms, right? Oh, also, don't worry too much about these 2 blue lines at the bottom yet. That's for a few weeks from now. We'll be talking about momentum. We're not quite there yet. Right, so let's look at these forms of energy, which each come with a certain expression, a certain formula. We're going to go through these one by one. I'll tell you guys exactly what they are and how they all relate to each other. Right, so work. Did I tell you guys work was a transfer of energy? Right, so capital W could be the variable, right? W for work. Right? You guys, does this mean watts? Is this watts here? No, Work and work is measured in, what is the unit for work? Joules. Yeah, joules, right? Now I can get that by force times distance. So if I push on something for some distance, then I've transferred some energy into, say, that object. And remember, you cannot create energy and you can't destroy it either, but you can transfer it. And this is like a transfer of energy. Right. Give you guys some examples. Right. Say, here's your largest lab mass. This is 1 kilogram of mass. How much does this weigh? How many newtons? 10. Yeah, 10 newtons. Right. You could also say 9.8. Actually, that'd be a slightly better answer, but I'm going to call it 10 newtons. Right. So to pick it up, does it take 10 newtons of force to pick it up? Yeah. Suppose I pick this up 1 meter. So let's say it was like sitting down on the floor and I lift it 1 meter and set it on the shelf. Right. So it took 10 newtons to lift it. I picked it up 1 meter and set it on the shelf. How much work came out of my muscles to lift it up 1 meter? 10 joules. Got 10 newtons times 1 meter. Isn't that 10 joules right there? Right? All right, you guys get that, right? Later on today, we'll look at, what if you push a shopping cart? What if you push a shopping cart with like 10 newtons of force for like 10 meters across the aisle, right? Because what is 10 newtons pushing force for 10 meters? What is that? 100 joules would be transferred into the shopping cart, right? So let's say that for later, right? But let's go back to this weight here, right? So I lift it, takes 10 newtons to lift it, right? And I lift it 1 meter, so that's 10 joules it took to lift it, right? I've got here, there's a bunch of things I want to say. I'm going to try to get these things in order, right? There's more I want to say about that, but let me show you guys the graph version of this, right? Suppose I lifted with a constant force all the way up, and I lifted 1 meter straight up, right? Here's the graph interpretation. Is force times distance could be the work transferred, and on a graph that would be the area under the curve on a force versus distance set of axes, right? You guys seen lots of graphs in this class. This is a new graph, but you see this graph all over the place in physics classes, right? Force versus distance. If you ever see a force versus distance graph, there's a really good chance you're going to get a question about energy or work. And it's just the area under the curve. In this case, it's very simply a rectangle shape, right? You see that? Okay. All right. So hold on to that idea. We're done with that. All right. All right. What about this? I'm going to change this up a little bit. So I'm holding this up with 10 newtons of force, right? Holding it with 10 newtons of force. What if I carry this 20 meters across the classroom? I bet this classroom's, well, let's say it was like 20 meters wide. And I carry this 20 meters across the classroom. Right? The fact that I'm holding straight up, but I'm moving it perpendicular to that, like horizontal, am I doing any work carrying it across the room? No. So to move it 20 meters across the room, how much work is that? 0 joules. 0 joules. Okay. Which brings me to this dot right here. You guys see this dot? Does this dot mean multiply? Yeah, force times distance, right? But it's a special kind of multiplication called a dot product. You guys hear that? Dot product? Dot product means this. It means you only multiply the parallel components together. So if I lift this straight up, right, now I am pulling straight up and it is also moving straight up. Okay, well, that's in the same direction. So that's why I was allowed to multiply 10 newtons times 1 meter and get 10 joules. I was able to do that. Right. Right. You guys ready for the next poster? Now, this one looks kind of complex at a glance, but let me break this down. This is going to make sense. Right. What if then, let's take this object right here. Here it is right here. It's like 1 kilogram right here. Right. I'm going to walk it up some stairs. Now, the lifting force I have to carry against its own weight. So that's like a force straight upwards. So this is like 10 newtons, right? Right. But guys, look at the distance that I'm moving it. It's like this diagonal. You guys see this diagonal? Now, just a moment ago, I asked you guys, I said, if I carry something across the room, and you guys said, how much work is it to carry across the room? 0 joules, right? The only part that really counts is in the same direction of the force that I'm lifting, which is the straight up part. So do you guys see carrying up the stairs? I really care about these two right here. So this force, kind of this upward component of the distance, right? And this upward component, well, playing off this angle between those two vectors, it's really a cosine component. Do you guys see that? So it's force times distance times cosine theta. You guys see that? Right? Or let's do the shopping cart example. If I push a shopping cart, now if I push a shopping cart straight forward, 10 newtons times 10 meters, that could be 100 joules, right? Right. But what if I don't push straight forward? What if I push kind of down and forward? Guys, is that downward component moving the shopping cart forward at all? No. Only the forward component is actually moving it forward. So that's all that counts for like the energy transfer, right? So that's like force times cosine theta. Here's the theta of between the two vectors of the force and the distance moved. It is moving forward this time, right? Okay. So the only energy that gets transferred, the only work I'm doing on the shopping cart is FD cosine theta, right? So because when you see this dot product, and this is a dot product, force dot distance, it's the magnitude of each of the magnitude, so force times distance times the cosine of the angle between them, right? Again, if they're all in the same direction, cosine of 0 is 1, so that you get 100% of the effect. If they're perpendicular to each other, like moving this across the room, you get nothing. Cosine of 90 is 0. Cosine of 90 degrees is 0, right? And then any angle between, you got to take the cosine, okay? Yes, careful, make sure you don't get this angle down here, then it turns from cosine into sine. I'm giving you the angle between the two vectors, okay? Yes, all right. All right, so you guys good on work as force dot distance? Okay, so that's an energy transfer, right? Now, I told you guys you cannot create energy, you cannot destroy energy. So if this started out on the floor and it lifted up 1 meter and set it on top of the table, right? See if you guys follow this, right? What if I put it right at the edge of the table and I give it a little bump and it falls off the edge? It crashes on the floor, crash. Because if it took 10 joules to lift it, what's the energy associated with crashing on the floor? 10 joules, right? It was 10 joules the entire time. It took 10 joules to lift it, right? Set it on the edge of the table, and then falls and crashes on the floor, also with 10 joules. So do you guys think while it was sitting at the edge of the table, that 10 joules is somehow represented, has something to do with its weight, but also its height above the floor? It's the same as the work I did lifting it in the first place, isn't it? Weight times height, which is exactly what this is right here, and that's called potential energy, gravitational potential energy. You guys see that? Right? So I'm usually going to use capital U, although, did I over here? Sometimes you see it as PE. Because if you see PE or capital U, think potential energy, right? And hey, look at this. The force I lifted it with was equal to its weight, mg, and the distance I lifted it is the height. Do you guys see that mgh just falls straight out of F times D? It's the same thing. This comes straight from this. This mg is kind of like this F. This h is kind of like this D. Is it? Okay. So this sitting at the edge of the table has 10 joules of this potential energy, right? 10 joules of potential energy, right? Which you get all of that crashed into the floor if you knock it off the edge. Right? Guess that too? Right? What else I want to say here? Oh, okay. And to connect it back to this poster then, right? If you walk this object up these stairs and set it at the edge of the stairs, point right at the very top, the amount of potential energy it has then is just mgh, right? So mg, which is the force to lift it, which is equal to its weight, right? Times this height, right? But again, it has nothing to do with how far you moved it across the stairs, only how much you lifted it up the stairs, right? So mgh, so it's got that type of energy. All right, now, do you guys see those different colored rows? I got a gold row, gold, green, gold, gold, green. You guys see that? Right. What I'm trying to do is help distinguish a little bit. These green rows are a little bit more abstract, a little bit deeper into physics. We're not going to touch these green rows very much, but mostly the gold rows, right? So what is this green row? I actually have 2 rows for potential energy. Let me show you guys why. Guys, 99 times out of 100, when I say potential energy, gravitational potential energy, you can just say mgh, and that's fine, right? But look at this lowercase g right here, gravity field. Let's think back last couple of weeks. If you send a rocket all the way to the moon, is this lowercase g constant all the way from Earth to the moon? No, it tapers off 1 over the distance squared. Okay, so then you need something different to represent potential energy. There's a more universal form, and it's this one right here, negative GMM on R. I might possibly explain that in the next few days, but we won't have time to get to that today. Right. But you can, if you show a very small change in height, it just very simply simplifies back to mgh, right? Which again, 99 times out of 100 in this class, that's all you're going to care about for potential energy, okay? Right. If you go from the top of Mount Everest down to sea level, this g is almost constant, so you can basically call it 9.8 meters per second squared. All right, guys, good so far? Good so far? All right, so make sure I can move on to the springs here. Yeah, it's about to be springtime. You see spring potential energy? So it's also U, but subscript S for spring, right? 1/2 kx squared. What is that? Hey, K, is that like a spring constant? You guys heard a spring constant? Here, let's do a quick demo for you guys. I got a spring right here. You guys see the spring right here? My ballpoint pen, I have a spring. I got a cartridge, and I got to press that spring. Guys, does it take some force to press that spring? Yeah, it takes some force. did it take some energy to press that spring? Good thing I ate breakfast this morning. Now I got some energy in my finger and my finger muscles. I can press that. There's a transfer of energy. And I know there's some energy there because I can get it all back. Watch this. Watch this. If I release this cartridge, it's going to pow. It's going to go straight up. Let's see how high does it go. Pow. Oh, almost all the way to the ceiling. I saw it all the way to the ceiling. Hey guys, when it's all the way up at the ceiling, isn't that a really high height? That's a lot of this potential, this gravitational potential energy, isn't it? That came from being stored in the spring at some point. Now, we're not going to quite do that experiment in class because this is a very pointy end and there's about 40 eyeballs in a class. But so try to keep those separate. But then you guys saw it for a demo. I guess I can do it here. You can see that. All right, so I saw a transfer of energy there. All right, so where am I getting this 1/2 kx squared from? And for that, we're going to go way, way back in this class to something called Hooke's law. Hey, look, it's an orange banner. Do you guys remember these orange banners from way back in the day in this class? Right? Do you remember Hooke's law? Now, Hooke's law tells you something about the force that it takes to compress a spring, right? Or stretch a spring for your spring scales. But I just compressed a spring, right? It says, guys, the more I compress it, the more force it takes to do that. And that's a linear relationship. You guys remember F equals kx from back in the day, right? Now, that's spring force. That's not an energy. But there is an energy associated with that, right? Because, guys, look at these axes, force versus distance. Where else have you seen force versus distance? Hey, earlier today. That's this graph right here, isn't it? Now, here I'm showing a constant force. So the area is just a rectangle, but that represents how much work, right? Well, compressing a spring, the force is building up. So it's not a constant force anymore. It is this diagonal line, right? But the area under the curve still represents how much work was transferred, how much energy was done compressing it, and therefore how much energy is stored in the spring, which is completely compressed, right? Or if you like, could you break this up into like 100 rectangles, tall, skinny rectangles, go like all the way across to add them all up, right? That's a math process called integration. But on this graph, it's effectively just the area of that triangle, isn't it? Right? Let's find what is the area of this triangle. So, guys, it's the area of a triangle, 1/2 base height. Is that right? Right. And the base is, well, x, just however much I compressed it. The height is the force, which is equal to kx. That's from Hooke's law, F equals kx, right? So I have a base of x and a height of kx. And the area, which represents the work, is 1/2 base height. So the x's combined, so that gives you x squared. Here's the 1/2 for the triangle. You got a k. So put it all together, you get 1/2 kx squared. You guys see that? 1/2 kx squared, right? That's where this is coming from. Spring potential energy, 1/2 kx squared. Right? You guys see that? Right. So let me really emphasize this point, is that at this point in the class, you have now two different formulas for springs. And students mix these up all the time, but they're totally different things. One is force and one is energy. You guys see that? The force it takes to compress a spring is kx. That's Hooke's law. The energy, therefore, stored in that compressed spring is 1/2 kx squared. That's energy. Right? Force is measured in what? No. Newtons. Energy is measured in what? Joules. Okay? Totally different concepts, right? Let's get that? All right, let's see what I got next here. All right. So there's one last main one last gold row right here. Kinetic energy. This is energy of motion. Energy of motion. So capital K, or sometimes you say KE. Do I have a KE over here? Yeah, KE sometimes you say. I try to use capital K, different conventions, right? Hey, let me go back to this spring example. Guys, when I press this cartridge down, I let it go. Pow! Right when it was leaving the spring, it was moving really fast, wasn't it? Ooh, that could be energy of motion. Or if I go back to this weight example, if I put this at the edge of the table and it falls off the table, that energy of crash, well, that's like a motion type of energy, where I guess right before it hits the floor, it's moving really fast. How fast? Right? Oh, here's the energy associated with motion. It's called 1/2 mv squared. Okay, like kinetic energy, 1/2 mv squared. You guys see that? All right. Let me try to prove that to you guys. I should say too, here, this proof I'm about to show you guys, here, it's right here. It's this one. I could not find this anywhere on the internet. I could not find this in any physics textbooks. So I kind of just made this one up, but it works. So we're going to run with it. Right. So I'm going to start with something called work energy theorem, which goes like this. Suppose you push on something with some force for some distance, right? Hey, that's transferring work, isn't it? Isn't that work? Transferring energy called work. right? Now, suppose you're not lifting anything upstairs, you're not changing the elevation. That means that all that energy went somewhere else. Let's say it goes into its motion. So let's say all the work you do goes into kinetic energy. You guys see that? Right? So that's gonna be like the first domino that's gonna tip over all these other dominoes, and it's gonna lead to this formula I'm trying to show you guys. Right? Ooh, do you guys remember? Guys, what does Newton's second law of motion say? It's a really short formula. How does it go? F equals ma. F equals ma. You guys remember that? Hey, I substituted that right there. You guys see F equals ma? Is that right? Right. Next one. Take a look at this acceleration right here. I'm going to go way, way back in this class to, you guys remember these three kinematic formulas? Right. You guys remember three kinematic formulas? Right. Oh, let me pick this third kinematic formula right here. Right. Let's do it. Let's say it starts from rest. So I'll have V final squared equals V initial squared plus 2AX. You guys remember that one? It's just the third kinematic formula right there. Right. Right. Let's say something starts from rest. Okay, start from rest means V initial is equal to what? 0. Go away. Okay. Let's say I solve for this acceleration right here. Wow. I don't know if there's something on the air or something. I don't know. I've got 3 pens. They're all not working. They're all full of ink. I don't know. We got what we got. Okay, so maybe this paper's weird or something. I don't know. But if I'm solving for this A, can I just divide over the 2 with the X? Does that look like acceleration is equal to V squared over 2X? Could that be like that? Right. Oh, what if I call this XD for distance? Is that okay? Can I call it XD for distance? Okay. Because that is the next substitution. That's that right there. You see V squared over 2D. And this D and this D. Guys, what happens to this D and this D? They do. They cancel out. They go away. Right. And if that's true, then what you're left with is, okay, I got an M, I got a V squared, I got this divided by 2, I moved that for, hey, it's 1/2 mv squared. Look at that, 1/2 mv squared, right? So that's the energy associated with something being in motion, right? Could be this about to crash land onto the floor, having followed some height. Could be you throw a ball. Could be this cartridge flying through the air at some speed. Could be, how about this? There's a car going down the road, and that car is like 1,000 kilograms, and suppose it's going down the road at like 25 meters per second. Could you calculate how much energy is associated with that motion? Right? And since energy is conserved, did that energy probably come from burning some gasoline to get it up to that speed in the first place? Yeah, right? And if it was twice the mass of a car, suppose you load it up with groceries, I bet it takes a lot more gasoline. Right? You guys see how this is going together? It's a new way of thinking about things. All right. Pretty good so far. Ooh, let me reset this thing. All right. All right, everybody good? Everybody doing all right? All right, I think we're ready to move on next one. You guys ready for the next one? All right, this right here. This is going to be the thought process for most of the puzzles you guys are going to be solving for the next couple of weeks. This right here. This is step number 1. You're going to write down, okay, well, how do you read this? What does this even mean? Okay, so if something's a closed system, there's different ways to think about that. One way is if there's no external force acting on the system, on the objects in the system. Okay, how do you read this? Guys, what does this literally say? What does the symbol mean? Like the sum of, right? The sum of energy initial equals, let's get rid of this. This is not doing it. Oh, it's clicking. Sorry about that. Okay. The sum of energy initial equals the sum of energy final. Is that right? So this is going to be the framework, the thought process to solve a bunch of these puzzles. Is that, we're going to pick some initial point and some final point. I might call it like point A and point B in a system. Maybe something's changing height. Maybe something's changing speed. Maybe there's a spring that's unspringing. It could be all of those, any of those. Right. Energy is conserved. Look at that. This is also saying conservation of energy. However much energy I started with in joules is however much energy I end up with in joules. Maybe a different location, maybe a different speed, maybe a different height, maybe the spring's unsprung, but it's the same quantity of joules everywhere. And I can use that to solve things. You guys see that? Kind of the big picture thought process. Right? We'll do some equations later today. Right? No, well, we won't quite get to today, but we'll do some of these eventually are open systems. Now, if there's an open system, there can be an external force acting on the system. which means that there can be work done on the system or work done by the system. That's why I have a plus or minus, right? So maybe you start off with some amount of energy, some of energy initial, maybe it's like 100 joules. And if you have like plus or minus 30 joules, then you can end up with some different amount of energy at the end. And then that energy can take different forms. It can take, let me give you guys a list of forms. Maybe any of these right here, right? And then you can solve for stuff. And again, we'll do some of these later today, right? See what we got next. Oh, actually, the next one's one of our first examples. You guys ready for the first example? So get a good look at this. We're going to apply this right now. Is right? All right, so let's go to, hey, it's back to Galileo. Drop them balls off the tower. And maybe I want to know, how fast are these balls crashing into the ground? How fast? You guys see it? Wait a minute. How fast are these balls crashing into the ground? I think you guys could solve this like a month ago with these formulas, maybe? Does this look familiar? Right? Because which formula, I may have asked you guys this question like a long time ago. Which formula did you use, first, second, or third, to be able to answer that question? Yeah, third. Yeah. Right. Because here's the height of the tower. Right. Here's the crash speed. Okay. Let's try it out. What I want you guys to see is that whether you solve it this way or the new way with conservation of energy, you'll get the same answer regardless. Right. And this new conservation of energy method, right now it'll look like, okay, it's just a different way to do it. Some puzzles you can solve faster using this new method. Some puzzles are like way simplify using this energy method. Right. Let's go back to the old way. The old way is V final squared equals V initial squared plus 2AX. Right, that's all right. Now that's straight off the poster, right? Here, all I did was say just copy pasted that right there. Right? I want to solve for crash speed. Right? Ooh, guys, in physics, what does this word drops mean? Means initial velocity is 0. Let's get rid of that. Okay. So V crash, we're solving for. See, that squared is equal to, all right, 2 times, oh, hey, guys, what special kind of acceleration are we talking about? Acceleration due to gravity. Call that G. And, oh, hey, what special displacement are we talking about? Height. Yeah, height H. So we go like that, right? Like that? Right? Oh, and now we're one algebra step away from getting the answer. All you have to do is do what to both sides? Square root. So V crash equals the square root of 2GH. Just like that. Right. Oh, let me make sure. Guys, did you guys write this in your notes? Right. V crash equals, I got a square root, 2GH, like that. Did you guys write that? No, nobody wrote that because you had to extend your square root bar over the entire inside expression. That's what you guys actually did, right? It's square root, it's this whole 2GH, right? You guys have seen this before. You guys seen this before, and you're going to see it again. Guys, this is never going away. I'll tell you where you're going to see this in the future. In the future, the next semester, we'll have a water tower some height. And there's going to be a hose going all the way down to ground level. And then you open up the hose and the water sprays out. Psst. How fast is the water spraying out? We're going to go through Bernoulli's principle, but guess what the answer is going to be? Square root 2GH, based on the height of the water tower, right? Okay, but I'm getting kind of ahead of myself. Let's do the conservation of energy. Are you ready for conservation of energy? Okay, so you know the answer to this question is square root 2GH, and you know that from kinematic motion. But what about this new method? All right, so let's think in terms of energy. So, hey, this ball at the top of the tower, how to get up there? Well, I bet Galileo had to lug it up there. You guys think, it took some work to lift it to the top of the tower, right? Right, and now it has what type of energy at the top? Potential. Yeah, gravitational potential energy. And what's the formula for that? MGH. Right. Oh, hey, that's kind of like weight times height, which is the amount of work that it did to take it up there in the first place. Okay. Now it has all MGH. He's reaching out. He's about to drop it. Okay. All right. And then he's going to drop it, and the ball's going to go all the way to the bottom. And right before it hits the ground, does it have height anymore? Basically, no. So all the potential energy is gone. Where'd all the energy go? Into what type of energy? What's energy of motion called? Kinetic. Kinetic. Isn't it moving really fast down here? with a bunch of kinetic energy? What's the formula for kinetic energy? 1/2 mv squared. That's right, 1/2 mv squared. All right, so there's the energy at the bottom. All right, so now we got energy at the top is all mgh, 100% mgh. At the bottom, it's 100% 1/2 mv squared. Well, 99.999% for that rate. Maybe it's like 1 millimeter above the ground. You guys get the idea, right? It's almost all this. All right. So, hey, guys, is this amount of energy equal to this amount of energy? Like, guys, if this is 115 joules, is this also 115 joules? Yeah, it's the same amount. Hey, yeah, it's different forms, but it's the same quantity. All right, are you guys ready for this? You guys ready for this? That's going to open up. Here, I'll just show you the whole thing. This right here. Here's your framework. The sum of energy initial equals the sum of energy final. That's to say, the sum of the energy at the top is equal to the sum of energy at the bottom. Now I'm saying sum of, but really it's only one type of energy at each point. It's all mgh at the top. It's all 1/2 mv squared at the bottom. Right? Guys got it? Guys, what variable cancels? The mass, m. Right? I think that's something I emphasized before too. You guys go work here. Go to the top of the tower. You drop these two objects off. Which one hits the ground first? Same time, which means that the mass canceled. So I bet the crash speed has nothing to do with the mass. All right, and that's what this also shows. Or in terms of kinematic motion, the mass never even showed up at all. Okay, go back over here, the mass cancels. Okay, and then if you solve for this v, what do you get? Square root 2gh. Hey, that's the same thing we got before. That's this one right here, square root 2gh. Look at that. It's the same thing. Right? Only now, looks like, yeah, look at that. Same thing. Right, you guys good? All good there. All good. All right. All right, guys ready for next one? Next one. Ooh, get more paper here. All right. So let's do something really similar to this, which is, this is not a whole lot different. Okay, let's throw the ball straight up. Okay, see that maximum height of a ball thrown straight up? Okay. What if, here, I'll give you guys two different stories, but they're kind of the same scenario. Okay. What if you throw a ball straight up in the air? You and some friends get together and start throwing some balls up. Like, who can throw the ball the highest? Okay. If you know how fast you can throw, do you think you can figure out how high you can throw it? Right? Okay. Or here's the reverse story. Suppose you and your friends are next to a skyscraper. Right? Well, let's have a ball throwing contest. I can throw my ball up to the 4th floor. Well, I can throw my ball up to the 5th floor. Well, my ball can hit the 6th-story window. Kids, get all the way. Stop throwing balls over windows. And if you know how high the window is, you know how many meters per foot, I bet you can figure out how high the ball's going. And therefore, you can calculate how fast you're throwing. So here's what I'm trying to get at. If you know how fast you can throw, you can know how high you can throw. Or if you know how high you can throw, you can calculate how fast you can throw. Okay? Now, I want to do this kind of like what we just did with Galileo, which is that I bet there's two different ways now you can solve this, and they better be giving you the same answer, right? So let's start with the old way. The old way is the kinematic approach. Because which kinematic formula do you think is going to solve it? First, second, or third? Because it's almost the same as Galileo. Probably the third one. Right. So let's start with the third one. Remember, the third one doesn't say anything about time. Do you guys notice that too? Is that here, if I'm kind of linking the new stuff to the old stuff. Oh, do you guys notice with all these energy formulas, I haven't mentioned anything about time, right? Except for power. Power is energy over time, but besides that one, right? So maybe that's a hint how all this energy stuff kind of relates to that third kinematic formula, right? Right now, if you want to solve for x based on h or h based on x, anyway, I plugged in some stuff. I got both answers here. So here's how high you can throw based on your throwing speed. Or right beneath it, here's how fast you're throwing based on how high does the ball go. Right? Oh, look at there's a square root 2gh showing up all over again, isn't it? Look at there, it's not going away. Okay. Now let's think in terms of energy conservation. Guys, energy conservation, what's the very first line you're going to write for almost every single puzzle you're going to solve the next couple of weeks? Boom, that right there. That's your first line. That's the first domino. That's the framework you're thinking in terms of now. And starting today, you say the sum of energy at one point equals the sum of energy at a different point. That's conservation of energy. Energy is conserved. Right? Now, those forms of energy are going to be different. Let's say throwing it. Because when you throw the ball, it's basically at ground level, right? Which means it has no potential energy, but it's moving really fast, leaving your hand. That's a lot of what kind of energy? Kinetic? Write down, guys, what's the formula for kinetic? Right there, kinetic energy. Okay? And then when the ball goes to its maximum height, how fast is the ball moving at the very top? 0 meters per second. And if it's not moving at the top, I mean, it's only for 1 instant, how much kinetic energy does it have at the very top? 0. All right. Okay. But so where'd all the energy go? Into what form? Potential energy. And can you guys write the formula for potential energy right here? Right? You guys got that? You guys got that? So we have, there it is. Is that exactly what you guys just wrote in your notes? You said it starts off with all kinetic energy leaving your hand and ends up with all potential energy at the maximum height. Right? Yeah, this looks a lot like that Galileo question. It's not a whole lot different. Okay. And then if you finish this out, here, I'll show you guys the rest of it. This goes like this. Okay. So if you solve for H, the mass of the ball cancels. So if you have a baseball and a tennis ball, if you get them to be leaving your hand at the same speed, then they'll go the same height. Okay. All right, something like that. Okay. Here's height in terms of throwing speed. And then right beneath it, I just rearranged it with algebra to solve for throwing speed as a function of height. But look at that. It's the same as with the old method. The old method, kinematic, the new method, energy. Look, we're getting the same answers. All right, you guys get that too? All right, that's good. That's good. All right, ready for next one? All right. All right, next one. This next one's fun because it has all the main forms of mechanical energy that I care about. Let's go back to this checklist here. Right. So again, we'll be solving lots of puzzles next couple weeks. Here are your building blocks that you care about. Okay. Again, not so much the green ones, but I'm going to mostly focus on the gold ones. Let's do a quick review. So work is force times distance. That can be an energy transfer. But if you're setting up a conservation of energy, it really kind of narrows down to these three, really. Here's gravitational potential energy, MGH. Here's, at the very bottom, is kinetic energy, 1/2 mv squared. We've just been working with those over and over. And if you bring in a spring, there's your 1/2 kx squared, right? Right. So now this one, I really like this poster because it's pretty all-encompassing for what we're talking about this week. Here's the story. I'm going to take some mass. I'm going to press it against the spring. Ugh. Guys, did it take some force to compress that spring? Yeah, in fact, I know it took more and more force the more I compressed it. That's Hooke's law, right? Therefore, how much energy is stored in that spring right now? As a function of K and X. How much energy? It's this right here. It's right here. It's 1/2 kx squared, okay? So the amount of force it takes to hold it there is kx, but you don't care about that so much. You care about the energy stored in the spring, which is 1/2 kx squared, which is also the amount of work that it took to compress it there in the first place, right? So good thing I ate breakfast this morning. I got some food calories, which is just a different way to quantify energy. And now my muscles are transferring energy to compress the spring. I'm trying to hold it there. All right, there's 1/2 kx squared of energy. You guys got that? All right, now I'm gonna let it go. Oh, guys, notice there's no friction on the track. You guys see that? No friction? Let it go. There's pew, flies around the track. Something like that. All right. Hey, is there some minimum speed to guarantee that it gets around the top of the loop? There is. We've been solving that last few weeks. I know it's equal to square root GR. Right? I remember that. Raised curvature, gravity field. Right. Maybe that could be my question. It's like, how much do I have to compress the spring to guarantee it gets around? Or what's the minimum spring constant? Or what's the maximum mass I could use? I could ask any of those questions. Okay. I need to pick a point A and a point B. And it's the same as the pictures on my poster. Right. So if I pick point A and point B here, it's set up a different equation. And I here's point A and here's point B. You guys got that? Okay. All right, so let's put this together. Right. At point A, it's 100% what type of energy? Spring potential. Right? And then let it go. Pew! At point B, where did all that energy go? Huh? What's that? Okay, so some kinetic, yeah, because it definitely better be in motion, because if it ran out of steam, it'd fall off the track. Okay, so I got kinetic, but also, guys, don't forget, to get up there in the first place, did it have to rise a height against gravity field? Yeah, and that's called what type of energy? Gravitational potential. So actually, that's both, guys. That's both types. You guys get that? Right. So here, let me show you guys the framework. Here's the framework to be able to answer this question. The sum of energy initial equals the sum of energy final, or point A to point B. So here's your initial point A, here's your final point B, right? Right. I want you guys to write the equation for that setup right there. Go ahead, write it in your notes. I'm going to take a quick trip around the classroom, see who's getting this. Write the equation that could answer any of those number of questions. What step to spring do I have to use, or how much do I have to compress the spring, what's the maximal mass I could use to guarantee it gets around the loop, something like that. Right? I need a conservation of energy equation to be able to answer any of those questions. What type of energy does it start with at the beginning? And what types of energy does it have at the top of the loop? Can you guys write the equation that can answer that question, or any of those questions? What's the equation? How does that go? Right. And because remember, all you're doing is you're just picking formulas from this page here, right? And really, almost all the time in the class, so you're just going to narrow it down to 3 of these. Here's your MGH. Here's your 1/2 kx squared. Here's your 1/2 mv squared. In fact, if you just use those 3, you'll get like almost all the questions right in this class for the next couple of weeks. Okay. So, all right, you guys ready? You guys ready? Right. What did you guys put for initial energy? 1/2 kx squared. Right. What did you guys put for the mix of final energy? It's both what and what? Yeah, it's both MGH to get it up to that position in the first place. And whatever's left over goes into its motion. We'll call that 1/2 mv squared. Right. So for example, let's add some numbers to this. So for example, what if it took 100 joules of energy to compress that spring? 100 joules. You guys got that? 100 joules? Is this number here like 100 joules? Then let it go. Pew! Suppose it takes 30 joules to lift it to this height. Is that this MGH right here like 30 joules? Right? Okay. Guys, if this is 100 joules and this is 30 joules, how many joules are left over to go into its motion? 70 joules. Ah, you guys get that? 100 equals 30 plus 70. You guys get that? Okay. And then, if you know, say the mass of this thing, and you know this is okay. I know this is supposed to be a 70 joules. I know the mass of this. Could you solve for v? How fast is it going? Absolutely, you can do that. If you keep track of the variables, there's 1, 2, 3, 4, 5, 6 different variables because m shows up twice, right? If I give you any 5 of those variables, could you solve for the 6th one? Yeah, let's do a little algebra. And that's the setup right there. All right, you guys get the setup? All right, I got one more poster for you guys today. All right, so that's this here. Now, so far how my class has been working out is I have time to just kind of look at this, kind of make sense of it, and then the bell's been ringing. So that's what I'll do with you guys. Okay. So, oh, hey, this is the video you guys saw at the beginning of class today. You guys ever see a bowling ball that goes around this loop? You guys saw it this morning, or well, at the beginning of class, right? And maybe have a couple of questions. One is, what's the minimum speed to get around? But that was something we answered like 2 weeks ago, right? And that's this gold box right here. Oh, look at that. V equals square root GR, right? We got that like a long time ago. Well, 2 weeks ago, right? Something like that. Now we're going to extend this question and say, hey, what is the minimum height of this hill that I have to drop this from so that it reaches that speed, so that it can get around? Okay. And I have a conservation of energy setup. So here, I'm just going to kind of leave this here so that at the end of the day, this always ends up being the answer. Because this is a really classic physics question. You can see it's a little complex. I probably squeeze as much as I can onto a single page, right? But this is always the answer. I bet some of you guys are going to take physics in college. And if you do, I bet you're going to see this exact question. And I'm telling you the answer right now. It's always 5/2 times the radius is how it works out. I mean, more important, can you actually go through the process and get there? But I'm telling you what the end result is. So for example, suppose this radius is 10 meters. You guys got that? If this is 10 meters, what is the necessary minimum height of the hill if there's no frictional losses? What's the minimum height of the hill to get around? 25 meters, right? Because 10 times 2.5. Okay, there's that. Right. Oh, actually, here, one more thing. There's one detail I forgot. I just want to fit this into this video. Right, one last detail. So let's go back to this one. Right. Do you guys see there was no friction on the track here too? No friction. Right. What I forgot to mention is that let's talk about the interaction between the track and the mass. You guys got that? Right. So as this mass is going around the track, is there a force from the track acting on the mass? Yeah, but it's not a friction force because that doesn't exist. It's or at least on this example. What type of force is it? Normal force, right? Guys, did I include normal force doing any work on the mass here? I did not. Let's think why that would be. Because, guys, normal force, by definition, normal means what? Perpendicular. But the motion of the block is always how? To the track. Parallel. Are those always going to be at right angles to each other? All the way around the track, right? And if there's a force and a distance that are perpendicular to each other, guys, what is the dot product of that? Always. What's the cosine of 90 degrees? Zero, right? So does the normal force ever do any work on a block sliding across the track? No, right? So that's why that's not part of this equation. All right, so that was a little detail there. All right, so that's going to have to be a pause point today.